Cesium and water. Most of us in science class will have seen what happens when a small piece of sodium is placed into a tank of water. In a short period of time, it begins to violently react, and if you're lucky, it may even explode. But sodium is only second on the list of the alkali metals, and if you look further down the periodic table, you'll see that cesium, with an atomic number of 55, is fifth. It's actually the most reactive of all the metals, and while it has a range of uses such as medicine, industry, and in scientific research, the best way to use it is to throw it into water and see what happens. In a similar way to sodium, when you cut into cesium, which is remarkably soft, you'll see it instantly react with the air and bright and shiny surface becomes dull and tarnished. When it's added to water, though, the reaction is virtually instant, and it's something that should only be done under controlled conditions with experts. It produces a huge amount of heat, will shatter most containers that this happens in, and is over in an almighty bang. While it's visually spectacular, the speed of the chemical reaction it causes is also lightning quick. By adding the cesium to H2O, it produces cesium hydroxide and large amounts of hydrogen gas, which explains the violence of the reaction, the flammability, and the power and pressure that it creates. Number 14. Briggs-Rauscher Oscillating Clock. The Briggs-Rauscher oscillating clock is a surprising experiment that shows that even when you think a reaction is complete, it may still have some way to go. As an oscillating reaction, the volume of each substance in the reaction is constantly changing, and this gives the impression that it keeps going backwards and forwards before it's finished. To create the effect, you need three colorless liquids: potassium iodate, a mixture of malonic acid and manganese sulfate monohydrate, and finally some hydrogen peroxide. With the potassium and iodate already in a beaker that's being mixed, the second liquid is added, and then the third, and the mixture will soon begin to turn amber in color. Suddenly it'll turn to a dark blue, but this will then strangely begin to change back to amber, then blue again, and this will repeat for up to 5 minutes before settling on the dark blue that smells of iodine. The reason why this happens is that the process that sees it turn blue and produce free iodine is only able to take place when there's a low concentration of iodide. As more iodine is created, the secondary process turns it into iodide, which means that the first process stops and the liquid turns amber again. At this stage, all of the iodine has been used up, so no further iodide can be produced, and when its concentration has fallen low enough, the process to make iodine begins again, and the liquid turns blue once more. In theory, this can continue happening for as long as there's enough of the constituent solutions remaining in the beaker, and it's a fascinating example of two reactions taking place at the same time, which directly impact the performance of the other. Number 13. Diethyl zinc and air. Diethyl zinc is a compound made up of zinc at the center, which is bound to two ethyl groups. It was the first organo-zinc compound to be discovered when it was first created in 1848, and is now an important chemical reagent that's used in a variety of applications. It is, however, extremely unstable when exposed to water or air, and this has led to a secondary use, where it forms a part of self-igniting rocket fuel. So to show this effect and the reason why it's so useful in rocketry, all you need to do is squirt some of the liquid into the air, and it'll ignite almost instantaneously. This makes it extremely tricky to store and transport, because just a momentary air technique. Number 12. Red phosphorus and bromine. Red phosphorus is one of the most common forms of phosphorus that you'll find, and on its own is relatively stable. There are strict controls surrounding the possession and purchase of the chemical, not because it poses an imminent danger to me. This means it's a lot rarer to see any reactions with red phosphorus, which is a shame, because it can be used for some incredible experiments. Probably the most impressive is when it's exposed to bromine or chlorine vapor, because in these environments, the otherwise inert substance becomes explosive. In the experiment, all you need to do is put some powdered red phosphorus in a jar and then pour a small amount of bromine liquid in. Even before the liquid makes contact, the reaction begins and will burn up all of the red phosphorus. When the reaction is finished, you're left with a yellow substance, which is phosphorus pentabromide, and some yellow vapor that's released. Needless to say, this is an experiment that definitely shouldn't be tried at home. Bromine in itself is dangerous enough to handle, and the gases that are released can be extremely toxic and will cause serious damage if breathed in. Number 11. Nitrous oxide and carbon disulfide. The reaction of nitrous oxide with carbon disulfide is often called the barking dog experiment, and once you see it, it becomes clear exactly why. For it to work, the nitrous oxide is put into a tube with a stopper at one end. A few drops of carbon disulfide are added, and then the stopper is replaced and it's mixed together. This allows for the vapors to form. Then when the stopper is released and a flame is inserted, an exothermic reaction takes place. A blue flame shoots through the tube, and there's a sound that's just like a dog barking. What's happening here is that a combustion wave is created that travels down the tube, and the blue light that's formed is a rare example of a chemiluminescent reaction taking place. The nitrous oxide acts as an oxidizer, and the reaction creates nitrogen, carbon monoxide, carbon dioxide, sulfur dioxide, and sulfur, so large that it injured the cheek of the Queen of Bavaria. Due to these potential dangers of the experiment, it's one that should be done in a lab with all necessary safety precautions. Number 10. Thermite and dry ice. Thermite is a mixture of finely ground metal and metal oxide, typically aluminum and iron oxide. It is often used in engineering because of its controllable explosive properties. Touching it with a flame will cause it to undergo an exothermic oxidation reduction reaction, whereby electrons are passed between two constituent parts and energy is released. Because the aluminum is highly reactive, it creates aluminum oxide and a huge amount of heat. But what's strange about thermite is that you don't have to expose it to a heat source to start this chain of events, and it can in fact be triggered by something very cold instead, like dry ice, and this can cause a violent explosion. Quite why it reacts with dry ice like this isn't fully understood. It's believed to be because the initial reaction releases a huge amount of energy that instantly turns the ice to vapor, which then oxygen, and it's these gases that cause the explosion when they're ignited by the heat. Either way, it leads to a spectacular effect, one that should only ever be done under controlled circumstances. Number 9. Elephant toothpaste. The elephant toothpaste experiment is visually amazing, and it's one of the best experiments that's safe enough to do at home. To create the effect, you need some hydrogen peroxide liquid, dishwashing soap, food coloring, water, and some yeast. To start with, you add the hydrogen peroxide, soap, and coloring into a plastic bottle and mix it together, while combining warm water and yeast in a separate cup. When you're ready, the yeast mixture is added to the peroxide mixture, and the result is a huge amount of foam being produced that looks just like what you'd expect an elephant to use as toothpaste. But why does this happen? Well, the yeast in the mixture acts as a catalyst, and this quickly breaks the hydrogen peroxide down and separates the oxygen from it. This produces a huge amount of small bubbles which combine with the soap and are filled with more oxygen than normal, so it expands extremely quickly. If you do this experiment for yourself, you'll also notice that the bottle gets quite warm. This is because it's an exothermic reaction. The foam that's being produced only contains water, soap, and oxygen, so isn't dangerous in itself, but we still wouldn't recommend trying to use it to clean your own teeth. Hit the like button. Number 8. Pharaoh's Serpent. If you've ever tried indoor fireworks, then you'll more than likely be familiar with the black snake experiment that produces a long tube of ash. But this is simply the safer and less spectacular version of something called the Pharaoh's Serpent, which was first discovered in 1821. By using a lump of mercury thiocyanate and applying a flame to it, you can trigger a chemical reaction that was described as winding out from itself at the same time to many times its former bulk out of a very light material of the color of graphite. There's no doubt that when you see it, that the ashes snake that's formed looks like the actual venomous snake of some kind, and in many ways the ash snake is equally as dangerous. The mercury thiocyanate is broken down into mercury sulfide, carbon disulfide, and carbonitride, while the main component of the ash is graphitic carbon nitride, which is yellow in color. Because of the toxicity of the gas and the ash that's produced, it's only safe to demonstrate the Pharaoh's Serpent in a fume hood to prevent anyone from inhaling the mercury. The black snake versions that you'll find in indoor fireworks boxes are only made up of sodium bicarbonate and sugar, so are far safer to be used at home. Number 7. Aluminum and iodine. You don't normally think of aluminum being a particularly reactive substance. After all, it's used in a range of construction processes. But when it's in the right environment, the results can be spectacular. To create aluminum iodide, the metal can be reacted with iodine by using water as a catalyst. For the experiment, powdered iodine and powdered aluminum are mixed together, and still at this stage they don't interact with one another. It's only once a few drops of water are added that things begin to happen, and soon there's a vigorous reaction. So much heat is produced that some of the iodine evaporates to create a purple plume of smoke, and you may even see some other colors forming too, if the aluminum starts to burn as well. It's the final product. Aluminum iodide is used in a range of chemical processes and is what's known as a Lewis acid, which, because it possesses an empty orbital, is actually able to actively absorb moisture from the air. Again, it's not an experiment that's safe to do at home because of some of the chemicals that are created. You most definitely wouldn't want to breathe in any of the purple smoke that forms. Number 6. Hot ice sodium acetate. As we all know, water turns to ice at its freezing point, and if you were to hold it, it would feel very cold in your hands. But what if there was a way to make ice that's warmer? Well, by using sodium acetate, you can certainly create the illusion that this is happening, even though you're not technically creating ice. This experiment relies on the principle called supersaturation, whereby you're able to load water with a large number of crystals, which will then collect together and form what looks like an ice formation. You probably know that there's a limit to how much sugar you can stir into water, but that if you warm the water up, you're able to dissolve more sugar into it, which will remain there even if the water cools down again. That's exactly how this experiment begins. Number 5. The Halloween clock. Normally, when you mix liquids of different colors together, you'd expect them to slowly change color. But there are some experiments where the reactions take place so quickly that an entire beaker of liquid will change color virtually instantaneously and almost look like it's a magic trick. One of the best examples of this is called the Halloween clock, or Old Nassau. To do it, you need a source of starch, sodium metabisulfate, mercury chloride, potassium iodate, and some distilled water. Already you can see that some of these ingredients are highly toxic, so this is definitely an experiment that should only be attempted with the assistance of experienced chemists. All of the parts are mixed together in a beaker, and the reaction begins straight away. To begin with, the metabisulfate ions react with the water to create hydrogen sulfide ions. Then these reduce the iodate ions to iodide ions, and once these are present in high enough concentrations, a mercury iodide solution is produced, which is orange in color, and instantly turns the whole solution orange. Things aren't over yet though, because a redox action then takes place and sees a molecular iodine being formed. And once this happens, the liquid turns a dark blue-black color instead. Named after Halloween because these are the two colors most associated with the celebration, or Old Nassau because these are the nitric acid and copper. Everyone's familiar with copper. It's used in the production of coins and is often used in plumbing and electrical wiring. The main reason why it's so common is that it's relatively inert and won't react too much with the environment. There are some chemicals that can get a reaction out of copper though, and one of them is nitric acid. The nitric acid causes the copper to oxidize, so to start with, after it's added, the solution is highly concentrated and takes on a green color. Soon after though, this will turn greenish-brown and eventually turn blue, but this isn't the biggest effect that's caused. At the same time, the nitric acid is reduced to nitrogen dioxide, which is a foul-smelling, poisonous brown gas that gets released in a large plume. As you can see in the experiment, the beaker is soon filled up with the gas and is carefully extracted, because if anyone were to inhale it, it'll cause some serious health problems. It's an experiment that's often shown at science demonstrations to highlight how even what seems like an unreactive substance can produce something highly toxic and dangerous, and it's the reason why the commercially available products that contain nitric acid will always have warnings on them about letting it come into contact with copper and other metals. Number 3. Sodium and chlorine. The next time you sit down for a meal, you probably won't think twice about adding some salt to it. It's a common type of seasoning that's used around the world, and we hardly even think of it as being a chemical. But its formula is sodium chloride, and it's made from two highly reactive elements. Sodium, as you probably know, violently reacts when it's added to water, and chlorine was used in the First World War. To do it, you need to fill a flask with chlorine gas, and one way to do that is by reacting hydrochloric acid with potassium permanganate. Once this is done, a couple of pieces of sodium are put into the flask, and a few drops of water are carefully put on top of it. The result is a bright flash and an exothermic reaction that produces a white smoke that's full of sodium chloride dust, which could then theoretically be collected and formed into salt crystals. The only question is, after seeing all the chemicals that went into making it, would you feel comfortable putting salt that's been made this way on your fries? Number 2. Nitrogen triiodide and touch. Nitrogen triiodide is a highly unstable inorganic compound. In 1812, the more common way of making it is by reacting iodine with ammonia. And when this is done at a low enough temperature in anhydrous ammonia, it creates stable and usable nitrogen triiodide. The reason why it's relatively unstable, though, is because its chemical composition involves a small nitrogen atom at the core and 3 iodine atoms held very close to each other. They're basically looking for any excuse to break these chemical bonds, and the first chance they'll get, they'll take. All you need to do is gently touch nitrogen triiodide and it'll explode with a poof of purple smoke. But beyond being amazing to look at, there are very few practical uses of it. This is because it's simply too unstable to be used in controlled explosives. Even nitroglycerin, which is similarly shock sensitive, can be altered to be safer to handle, but there's so far no similar process that can be done to nitrogen triiodide. To demonstrate just how delicate it is, you don't even need to touch it with something of significant weight. A feather is enough, and so is a slight breeze, the light of a laser, and even a quiet sound wave. And is also known as the only chemical explosive that detonates when it's exposed to alpha particles and other products of nuclear fission. Number 1. Dancing gummy bears. Gummy bears are undoubtedly one of the most fun treats you can get, where there's a reaction that can make them even more entertaining. Imaginatively called the dancing gummy bear experiment. It's possible because of the high sugar content of the sweets, and this is one that must only ever be attempted with the assistance of experienced chemists. It goes as follows. An ignition tube is filled with a small amount of molten potassium or sodium chlorate, and the brave gummy bear is dropped on top. Almost immediately, it produces a huge amount of purple smoke. The gummy bear can usually be seen violently jumping up and down inside the tube, and then there's a bright light as the gummy bear is fully consumed by the reaction. Rather than one process happening, there's actually a series of things going on here. At first, the potassium chlorate is melted, which is an endothermic process. And then this molten potassium chlorate begins to decompose, which releases oxygen. This at first produces potassium perchlorate, which then breaks down and then allows for the sugar inside the gummy bear to undergo rapid oxidization, which produces carbon dioxide and water, along with a huge amount of heat and light. The purple smoke has nothing to do with the gummy bear, but is actually the remnants of the potassium. It's a great experiment to demonstrate the energy that's stored within sweets and any other products that have large amounts of sugar in them.